As we discussed some 8-9 months back, the idea was to give a small course on parameterized algorithms, and the field has developed so much that 4 lectures are not enough to give you a flavor of what was happened in past and what is happening now in just 4 lectures. So after long discussion, we decided to give you a set of algorithms for longest path, or set of developments which has happened around longest path, and show you some old tricks as well as some new tricks which has been introduced, and on the way give you a flavor of set of open questions which exist in this area at this point of time. And so what I will do is that in my first 10-15 minutes, I'll give you some basics of parameterized algorithms, in the sense what is the kind of algorithms we are trying to design, and I'll give you a bit of historical perspective, and then I will talk about recent techniques to design parameterized algorithm, which is called representative sets. Now, we'll get back to this, that in my title says long path in 80s, but I'm going to give you a trick which was developed late 2010 or last 2-3 years, and we'll see how they're connected to each other. Okay, so by the way, parameterized complexity came primarily defined in 1990s, 89 to 1992. So when I talk about algorithm for long path, it is pre-definition of parameterized algorithm. So that is something to keep in mind. Okay, so the 3 problems which I would give you use as an exposition to set you up for all the tricks and techniques are problem on vertex cover. What is a problem on vertex cover? So it's a graph and a number k, and you're looking for a vertex cover of size at most k. And what is a vertex cover of size at most k? It's a subset of vertices whose size is at most k, and every edge contains one of the endpoint of this edge. Or in other words, if you delete this vertex from the graph, what is remained has no edges in it. So it's an edgeless graph, or it's a set of isolated vertices. And 2 problems which will be fundamental to our study is Hamiltonian paths, which I hope all of you are aware of. You're given a graph and you're looking to find, is there a path which contains all the vertices? And the decision version of this question is called longest path, where you're given a number k and you're asking, does there exist a path p in G of length at least k? And what is common in all these 3 problems are that all of these 3 problems are NP complete. So we have gone from the world of polynomial time solvable problem to world of NP hard problems. And the moment we go to the NP hard problems, we either need to worry about that, okay, we cannot get the solution exactly, so we have to lose on the precision, or we have to relax ourselves in the amount of running time which we demand to solve the problem exactly. So the paradigm which we will talk about now is of the second nature, where we relax the running time requirement. And approximation algorithm is where we still demand that the problem must take polynomial time, polynomial in the input size, but we are happy to get a solution which is as close to it possible to an optimal solution, or we are able to prove that such an object cannot exist. Okay, so now what is fixed parameter tractable algorithm? So now this paradigm has 2 aspects to the input. One is the input size, and the other is the number k, which we call that this is the aspect of the running time where you could be exponential, or it could be super exponential, or whatever you like to be. So the f of k could be, for example, 2 power k, for example, or f of k could be 2 power root k, for example, or f of k could be any function which you can imagine. But in the input size, which is the size of the input which is given to you, you are still allowed to be completely polynomial. And by polynomial, it should be the independent of k. So it should be like n square, so it should be n square, n cube or n cube, or n cube. This polynomial dependence should not depend on k at all. So it is completely independent of k. And algorithms for which we can make such an algorithm, right, are called fixed parameter tractable algorithms. For example, let's look at what are parameters, for example. So if you look at a vertex cover problem, the number k is a parameter. So we are trying to design an algorithm which could be some f of k but say linear in the input size, or some f of k but quadratic in the input size. Similarly, for the longest path, we would like to have an algorithm which, given a graph G and a number k, checks or tests whether there exists a path on k vertices or k edges. It does not matter how you define, they just differ by 1. And we would like to have designed an algorithm where there's f of k into polynomial in n. Okay? So is the goal clear? Right? Even if you don't remember the definition, it wouldn't matter at all for the discourse in this lecture, because all the time I will tell you, given this, I'm going to design an algorithm with running time this, and we will see how that algorithm is designed. But just to get a flavor, these are the kind of questions which we are interested in parameterized complexity. And look, there are many more aspects to input. Now, k is just the solution size which we are seeking. But the input could be number of vertices, the parameter could be just number of vertices, or the number of edges, or some structural parameters related to the input. For example, is how close this graph is to trees, because on trees, we know how to design several algorithms which runs in polynomial time. So for example, this will bring notions of tree width, or notions of feedback vertex set, how close I am to an acyclic graph, and things like that. Okay, so your parameter could be anything. So finding a right parameter by which you can design good algorithm is also an art, and people design several algorithms for the same problems, and maybe some algorithm could be useful with respect to some parameter, because for certain inputs or certain aspects, maybe those classes of input, this parameter is small. For some other set of inputs, some other parameter is small. So it is like I can make a family of inputs, and for which I will search what kind of parameters can span this whole instances, and try to design an algorithm with those parameters. And we hope that basically we will be able to cover this whole set of inputs with some parameter which is small, but it may not be the case. So the second question is, are we able to design an algorithm with running time f of k polynomial in n always? Well, no algorithmic paradigm is interesting if you always can answer yes, 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 yes. I mean, what's the big deal about it? No, you can also show that certain kind of algorithm is absolutely not possible. In fact, we can also show for several problems that some particular kind of running time, like n choose k, is optimal. Of course, under some complexity theory assumption. Sometimes we can say, so an algorithm which runs in time 2 to the power k, but 1.999 to the power k is not easy to obtain unless some bad things happens. And we'll see what do these bad things mean as we go forward. Okay, so I hope I have given you some example, I have motivated you. Another thing which is very interesting, and which I will touch upon in my last lecture, is the notion of kernelization, or notion of polynomial time preprocessing. What is this notion of polynomial time preprocessing? So this is a paradigm which is, again, here in this paradigm, you're given an input, say for example for vertex cover G and K, and you are asked that, look, you're allowed to use polynomial time, but reduce the data or reduce the input to as small as possible. For example, all of you have done, say, look at SAT formula. If a sum literals occurs all positively, then do we need to worry about this? No, we just set it to positive and we just reduce the instance to something smaller. If some literal occurs all negatively, then we do something accordingly. So we always use preprocessing or polynomial time algorithm to reduce the input size. Now, if the problem is NP complete, we cannot expect that we started with an input and every time we shrink, we shrink, we shrink. Because if every time in polynomial time you are able to shrink the input to something strictly smaller, then after polynomial time, the size of the instance will become constant. Now you can run any algorithm and it will still, and I can solve my problem. So we do not hope that for hard problems, we will be able to design such an algorithm. So generally people use heuristics, but there is no way to mathematically say that this heuristic is better than that heuristic. And what does fixed parameter tractable algorithm provides is a mathematical framework to study such algorithms. And what do I mean by this? First of all, it's a polynomial time transformation that transforms any given parameterized instance to an equivalent instance of the same problem with size and parameter bounded by a function of the parameter. Now, that's a mouthful, so let's just go what it means. So you have a language. So look, Classically, language is always a subset of sigma star. But notice that, as I told you, in parameterized problem, we have an instance and we have a number. So any instance looks like a subset of sigma star cross natural number. Okay? So given this x comma k, we have to run this algorithm in polynomial time. So p of mod x plus k, and return a pair x prime k prime in sigma star cross n, such that, what is the property? If you started with an yes instance of a problem, you still have an yes instance of the problem. And if you started with a no instance of the problem, you still have a no instance of the problem. So you have not changed the answer. But what I'm demanding is the size of the reduced instance is upper bounded by some function of k alone. So imagine that if I given you an instance x and k is like 10, all you are saying that in polynomial time, give me an instance whose size only depends on 10, so f of 10, so it's like constant, right? And then we can do something interesting about this. And where f is an arbitrary computable function, but p is a polynomial time algorithm. So this is where, you know, like, what is this? Like, okay, either you reduce strictly, that's great, you are making progress. But if you are able to show that, no, none of my reduction rules or none of my preprocessing rules apply to make this instance something smaller, then I'm able to prove to you that, look, well, you cannot do anything more, but the size of what is left is something very small, and by small is some function of k. Okay. And what is a polynomial kernel means? Polynomial kernel means that this f of k is some polynomial function of the input. Okay? Just to give you a flavor of this, let me give you one simple example before we do harder examples of things. Let me give you an example for vertex cover. Okay? So remember, what was the problem of vertex cover? Is that you're given a graph G, you're looking for a subset of size at most k, such that every edge has at least one of its endpoint in this set. Now, if there is an isolated vertex, a vertex which is not adjacent to any edge, do we need that for any vertex cover? No. So we can just throw this. So this is what I mean by preprocessing rule. And this is correct. So after I threw this, if G had a vertex cover of size at most k, if and only if G minus V has a vertex cover of size at most k, because this vertex was not responsible for any edges. So this is fine.
So how does fk looks like in this case? Because your graph has like n vertices and
yes.
you're moving just one.
Yeah.
You don't have this constant bound for. You don't have an fk bounding this size of your
I'll bound for you in the next minute.
Sorry?
I'll give you a bound.
Okay.
I'll tell you that when none of these reduction rules apply, the instance is already small. So that is where you need a combinatorial insights to bound the size of the reduced instance. So I'm going to apply some simple reduction rule, and by the end of this process, either I will be able to tell you, look, this is a yes instance of my problem, or I tell you this is a no instance of my problem correctly, right? Or I will give you an instance with a guaranteed upper bound on its side.
Okay, so this fk doesn't apply to one particular step. You have to do these several
steps. Yes. So this is a polynomial time algorithm. This is a step in my polynomial time algorithm. It will have several more steps, because if I just do this, come on, if you give me a graph which does not have an isolated vertex, this does nothing. Yes, but I have a simple, interesting reduction rule. Suppose if I have a vertex V whose degree is more than k plus 1. What can we say about this vertex V? Right? I have a vertex V which degree is like greater or equal to k plus 1. What happens if you don't pick this red vertex into a vertex cover of size at most k? What can you say? Exactly. But how many of them are there? At least k plus 1. But what were you looking for? A vertex cover of size at most k. So if you decide not to pick this vertex into your solution, there is no way you can get a vertex cover of size at most k. So what is our reduction rule? Reduction rule simply says, okay, let me go back. Okay, so include V in the solution, delete V, but now we are not looking for a vertex cover of size k. We are looking for a vertex cover of size k minus 1, because we have made a correct decision on a vertex of size V. So we apply these two reduction rules one by one. Like these are polynomial time, because look, every time the size of the graph is decreasing. When you are throwing an isolated vertex, n decreases. When you are deciding to put a vertex into your vertex cover, size of the graph still decreases. So clearly, if I apply this rule 1 and 2 exhaustively, after polynomially many steps, I will stop. And each of these steps can be applied in polynomial time. Okay.
Do you have to follow this order first?
No, it doesn't matter, whichever order you want to. But sometimes it is important, for some algorithms, it is important that you have put down these steps and you have to follow these steps in a particular order. Because if you did this 1, 2, 3, then you can say, hey, then such a property will always exist and which we can exploit. So apply these rules until no longer possible, and I do not tell in which way you apply. So what conclusions can we draw? See, if G is not empty and K drops to 0, what can you say? So you're looking, a graph has an edge and you're looking for a vertex cover of size 0, then I can say no, right? Then by just looking at this question, I can answer immediately that it's a no instance. So what can I do? I can return an equivalent instance which is a no, which is like I put an edge, a 0. It's clearly a small trivial no instance, and that is what algorithm can return, an equivalent instance which is of constant size. Outcome 2, why did you stop? Because every vertex has degree at most k. Because if you had a vertex of degree greater or equal to k plus 1, you would have applied reduction rule 2. Now, every vertex has degree at most k, and you're looking for a k-size vertex cover, then how many edges can it cover? If one object can cover k things can cover k square things, right? So number of edges they can cover is at most k square. So what can we say if the number of edges is strictly more than k square? The answer is no. So if the number of edges was more than k square, we still say no. So the number of edges is less than or equal to k square. Now how many vertices a graph can have? There are no isolated vertex. So every vertex is adjacent to some edge, right? So if the total number of edges is k square, total number of vertices is upper bounded by 2 times k square, even if all these edges are some matching edges or something, right? So what do we have? We have a polynomial kernel of size order k square. Now it might sound something very fishy or something, but let me make a statement without any justification. So this is the first thing which we teach people in parameterized algorithms. Whenever I teach a course, this is the first thing which I teach. And I tell at the end is that, well, you cannot do better than this. In terms of the total size, in terms of reducing the number of edges, this is the best you can hope for. Because if you can get a kernel with, say, number of edges being k to the power 1.999, how many over 9 you want, if you are able to do this, then in complexity theory terms, polynomial hierarchy will collapse to some second level, or I think third level, or some level it will collapse, which we do not believe to be. So you can prove. So this was the easy part, but the hard part is, which we were able to develop after 20 years, machinery which is able to show that anything which is better than this, k to the power 2 minus epsilon, for any fixed epsilon, if we are able to achieve, then the polynomial hierarchy will collapse to the second level, which is like, which will not happen before Earth collapses. So we should be perfectly fine and do not try at all. Okay, so this was my example of a vertex cover. I hope you people have understood. This is what I mean by a polynomial time algorithm, which gives me an equivalent instance and whose size is bounded. So the next question which we always ask is that, given a parameterized problem, are we always able to get a kernel which has size polynomial in k? Well, for that also you have a different set of answers. Sometimes we are able to get kernel with size k power 100, and then we ask ourselves, is k power 100 optimal or k power 99 is possible? So till you are able to not prove a tight lower and upper bound, the game still remains. And that is a kind of question which has been played quite a lot in last 4 or 5 years. Okay, so this is what about kernelization, but I have not even told you an FPT algorithm yet. So is vertex cover fixed parameter tractable? Now if I tell you that now that I have given you a kernel, why did I teach you, right? So if I now ask you, is it possible is testing whether there exists a k-size vertex cover, does it admit an algorithm with running time? Yes, no? Can you deduce something from here? What did this tell us? It gave me a polynomial time algorithm, which if it says yes or no, we say yes or no. That's perfectly fine. Otherwise, in polynomial time, we have got an instance whose size is bounded by number of vertices is 2 times k square. Right? And now I'm asking you, is there a vertex cover of size at most k? So what is the most trivial algorithm you can think of? If I give you an n size graph and I say, test whether it has a vertex cover of size at most k or not, what is the most obvious algorithm you can try?
Tasting all the subsets?
Try all possible subsets, right? But that algorithm will run in time n choose k and maybe some n square time to test whether it is a vertex cover or not. But after we have applied this procedure, so maybe this procedure takes some n power c plus. Now what is n? N is upper bounded by 2 times k square. So we have an algorithm which runs in time 2k square choose k, and I will forget the polynomial factor. But this is some function of k, right? So we do get an FPT algorithm when we have a polynomial kernel. Try a brute force, right? But what is amazing is that a problem has a kernel, maybe of arbitrary size, if and only if the problem is fixed parameter tractable. So if they have a kernel, we know this. But if they are fixed parameter tractable, why do they have a kernel of any size? Requires some bookkeeping kind of argument, and which I will not tell you in the lecture. Okay? Is the idea clear at least? That vertex cover is definitely fixed parameter tractable. Try all possible subsets. But before that, make sure that you have run your simple polynomial time preprocessing. Then your brute force algorithm is actually a fixed parameter tractable algorithm. Okay. So that brings to me, now I'll go down to the historical development of longest path. So I have defined 2 things up until now. What do we mean by fixed parameter tractable algorithms? What kind of algorithms are called fixed parameter tractable algorithms? And what does polynomial time preprocessing mean? Now, let me tell you how this longest path came. So as I told you before, it was known, the parameterized complexity, the way I defined to you, was defined in the paper by Downey and Fellows, I think in 1991, something around that point of time. But algorithm for k path was much, much before. So you just now gave me a naive algorithm for finding k size vertex cover. What will be a naive algorithm to test whether a graph contains a path on at least k vertices? What is brute force?
Check for permutations.
Of
Edges.
Of size how much? Of size how much?
Just key.
Okay, so what it will be the running? What will it constitute as a running time?
Exponential.
But what? It's okay. What exponential? I'm perfectly fine with this. So there are m edges. There are k m edges, out of which you choose k edges, and you try. Right? So it will be n squared choose k, because m could be as bad as n squared, and some k factorial because you have to check. But the better algorithm could be slightly better, not anything better. You choose the vertex, k vertices, and look at their permutation. Right? So I choose k vertices, and I look at their permutation. Once I fix the permutation, I check, is there an edge from the first vertex to the second vertex? Is there an edge from second to third vertex? And so on and so forth. Okay? So this is the algorithm which will run in time n choose k and k factorial. And this is what I mean, a naive algorithm. Okay? Unfortunately, we cannot play tricks the way we did tricks before, that we first got a polynomial time preprocessing and bounded n by some polynomial function of k or any function of k. Unfortunately, we cannot do such tricks with longest path, as we will see in the 4th lecture, that finding a polynomial kernel for longest path is not possible, and again, unless complexity theory hypothesis fails. But in 1985, Moonin had an algorithm which had running time k factorial times nm. And if you notice, this is an FPT algorithm, because k factorial is a function in k, upper bounded by k to the power k. And from 1985, this algorithm was there. And so what does it imply? If you look what does it imply is that this is basically which basically is, if you think of this, is k power k nm algorithm. Now, if I ask you a question, is there a longest path of size at least say log n divided by log n? Then what happens? If you do here k, so let's call this, basically this is 2 to the power k log k, because k is nothing but 2 to the power log k. Now, if you substitute k equal to log n by log n, then you will get something like 2 power log n divided by, no, what am I writing? Log n divided by log n. And what is log of k? Is roughly again k log k. So k is log n by log n. So what you will get is log n minus something. So log n will get cancelled, and 2 power log n is nothing but polynomial. It's linear. So depending on if it have been 2 log n, you will get something like n square or something. So what does it mean? That in fact, some of these algorithms can be used to test things up to logarithmic, whether there is a polynomial time algorithm or not. And this was a question which was asked by Papadimitriou and Yannakakis, where they were trying to understand, is finding logarithmic version of problems polynomial time solvable? Like, for example, given a graph G, does it have a vertex cover of size at most log n? Is it polynomial time solvable? So they similarly asked the question about k path. Is the given a graph G, testing whether a path of length at most log n exists or not, is it a polynomial time solvable? So this is a paper which basically looks very similar to kind of notions we use in parameterized complexity, and this is a conjecture which they made, that testing whether there is a path of order log n is in polynomial time or not. And later, which we'll see, Allen, Euster, and Zwick gave an algorithm which ran in time 2 to the power big O of k times n to the power c. Now, what does big O of k means? If you substitute k equal to log n, what is 2 to the power big O of k? 2 to the power big O of log n is nothing but 2 to the power some constant times log n. So it will be n to the power that constants times some n to the power c. So they actually settled this problem, and we will see this algorithm. It's very simple algorithm, very beautiful algorithm. And the method which was invented is called color coding. It appeared in JSM 1994 or 95. Very beautiful trick. And so this is the starting point of all algorithms for FPT, okay, on long path. So we have this k factorial algorithm. There was an algorithm in between which I skipped for some reasons, and we directly came to this. And you can show that you cannot even test whether there is a path of length log n to the power 1 plus epsilon in polynomial time unless some complexity theory fails. Okay, so this is the best we could hope for. Now in 2007, so after 1995, so this 2 to the power big O of k, if you really unravel the running time, is basically like 2e to the power k, like where e is a natural base of log. So this will be something like 5.7 to the power k. And now people have tried to optimize this as small as it possible. Yeah, I think 2e will be like some 5.7, no? Or 5.4. Oh. I think it's 5.4. Because like e is like some 2.7 something something. So fine. Okay. So in 2007, Chen, Nies, Liu, Moll, Richter, Rosenmuth, blah blah, they came up with a new algorithm which ran in time 4 power k. So that the technique which was invented is divide and color. We will see this also. Okay, so this is my first open problem to you. The good thing about this algorithm is that it runs in polynomial space. Okay, so amount of space it stays is polynomial in the input size, A. B, it is deterministic. But we do not know any algorithm, even 3.99 to the power k algorithm, which is deterministic and runs in polynomial space. So this is my first open problem to you. Okay? I don't think it's very hard. It's just that maybe people have not thought from the right perspective. So if any of you are interested, I'm quite sure if you think sufficiently enough, or maybe one day, how lucky you are, I don't know, you should be able to crack this problem. I think this is the easiest of all the open problems which I will ask.
What about randomized algorithms?
We'll come to that. I'm telling you history. So let's go chronically. In 2008, Ioannis Koutis came up with an algorithm 2.83 to the power k, n to the power c time randomized algorithm. Okay? And what was the technique which was developed? Was called algebraic methods, which we will spend a whole lecture on, this algebraic methods. But very soon, that algorithm of Koutis was improved by Williams to 2 power k n to the power c time algorithm. And that was a very nice algorithm by Koutis using group algebras and all. And Williams immediately improved that algorithm, like doing much more of group algebra. We will not see this algorithm in this course, but we will see slightly different algorithm which will achieve 2 power k. Basically, you can think of this as a reinterpretation of these algorithms. But in 2013, Bjorklund, Husfield, Kasky, and Kovista came up with an algorithm which running time is 1.657 to the power k, still randomized. And this happens to be the fastest known algorithm for, and the technique which was invented is called narrow sieve. And we will spend whole one lecture on this. And this is still the fastest known algorithm, though randomized, and works only for undirected graph. So if the input is directed graph, and I give you to find a path of length k, all other algorithm works up till 2009, except this algorithm. This algorithm works only for undirected graph. Okay, so the first open problem is design an algorithm for longest path running in time 1.657 minus epsilon to the power k if you can, because this has been now known for last 4 or 5 years without any improvement. So if you're able to do this, it will be great. Again, this in the setting of randomized, what space you take, I don't care. And even for undirected graph.
Is there a lower bound for the formula?
No. Sub-exponential. You cannot have 2 to the power little of k algorithm. Like maybe k divided by log star k is not possible, but not on the base of the exponent. Okay. So more interesting problem is design an algorithm for longest path running in time 2 minus epsilon to the power k for any fixed epsilon greater than 0 on directed graphs. K might look harder. So let's relax the problem. I'm telling you, if I give you a graph on n vertices, directed graph, this is for directed graphs. I'm happy with an algorithm with running time 2 minus epsilon to the power n, where n is number of vertices. Even this is open for last 7-8 years. In fact, any algorithm better than 2 power n, n is number of vertices, was open for long time. Before in 2010, Bjorklund came up with a very beautiful algorithm which gave this. So only Bjorklund came up with an algorithm which ran in time 1.657 to the power n, where n is number of vertices. And after a couple of years, they were able to make this n as a k. If you notice, k is much smaller compared to n. So for example, if you have a k, it automatically implies an algorithm with running time n, because any Hamiltonian path can use at most n vertices. So 1.657 to the power n comes for free once you have a parameterized algorithm. Okay? But for directed graphs, world is still wide open. We do have some small progresses. For example, recently people had designed an algorithm with running time 3 times vertex cover of the graph. Okay? Vertex cover of graph. Now, if I give you a bipartite graph, what is its vertex cover? Directed itself. And still you want to touch every. What is a vertex cover of a bipartite graph? It is upper bounded by n by 2. Take one of the sides which is smaller. So that automatically implies 3 to the power n by 2 algorithm, which is like 1.732 to the power n for bipartite graphs in terms of n. So there are some, I think this will appear in iCalc 2000. 17. And previously, people had made some randomized algorithm for directed path on bipartite graphs. But for general graphs, we don't know anything. Maybe 2 power k is in.
Second, but we only know this result in terms of n, not in terms of k.
No, we only know in terms of n, we don't know in terms of k. Even for directed bipartite graph, we don't know any algorithm which is better than 2 to the power k in terms of k. This we only know in terms of n. So for example, if I could replace on directed bipartite graphs, even then designing such an algorithm will be an interesting step forward. Okay, so that's my open problem. Next, let's move. So in 2014, with Feder and Daniel, we came up with an algorithm which ran in time 2.83 to the power k, but it was a deterministic algorithm. So it was the first time an improvement after 2007 to come up with a deterministic algorithm which ran better than 4 to the power k. But look, this algorithm matches the running time of Curtis. And just very soon we saw that our methods can be, so we did what is called fast computation of representative families, which if we have time, we will see a little bit. But very soon, we were able to realize that our method can actually be modified a little bit and can give you a 2.618 to the power k algorithm. And Merav Zihabi, later in 2014, came up with a slightly faster algorithm with running time 2.597. And basically, what she did is basically she took algorithm here, applied algorithm from 1995, applied ideas from 2007. So it's like really she mixed everything which was known for deterministic k-path in one algorithm. So like she realized, okay, here is where this algorithm works bad. Okay, so let's get rid of this. Okay, but then the other algorithm works much better. So let's do some massaging here, this. But it's a very complicated but very fine balanced algorithm which runs in time 2.597, which just tells us that 2.618 is not something magical. So this is the fastest known deterministic algorithm for k-path.
And it uses exponential space?
It uses exponential space, which is still the fastest known deterministic algorithm, though takes exponential space. All these algorithms based on representative families take exponential space, as we will see why it takes exponential space in this set of lectures. Okay, so 2.45 is just my arbitrary number, not something which I thought. It's just that please try to, if at all you try to improve this algorithm, try to improve significantly, not take her algorithm, find 10 more cases, and improve on those 10 cases. That's not interesting because you're not going to discover something new. But maybe if you try to improve significantly, by significantly, it's not too significant, but still, I believe the moment you push the bar slightly below, generally longest path tends to give you a new set of tools or new set of techniques. Okay? So let me tell, as I told you before, this list is not comprehensive and I have left out algorithms based on tree width. We'll speak about it if time permits, which I don't think, but still, okay? Because I did not want to introduce the term tree width because it requires its own set of lectures and so. So do you have any questions up until now? All I did, introduce fixed time retractability to you, gave you a history of long path, told you some set of open problems, and all I will tell you is the methods which had been used previously to solve all these algorithms. We'll definitely see a complete sample of all this. That's my whole goal. I don't know how much I will achieve, but that's it. And the type of lecture will be primarily, I'll try to give you all details because I really don't know at times how much detail should be told or how much detail should not be told. But I'll try to give you all the details for many, many things. And there will be one lecture which will be more like a survey talk where I will just brush over the remaining techniques or tools. Okay, so first, let's go the lecture mode. And by lecture mode means you can ask any question at any point of time. If I go fast or I go slow, please tell me so that I can adjust myself accordingly. My objective is not to fill you with all the things because whatever is remaining from these lectures, I will fill you anyway in my survey talk, right? So whatever you can learn at this point of time, please ask questions. Okay. So the longest path was in 1985. I told you Monin, k factorial nm time algorithm. And techniques we will see is representative families and sets. So basically this approach which I'm going to talk about, which we revisited later in 2014 and did lots of things, but actually was the first tool which was used to solve k-path as way back in 1985 by Monin. So we will see what this tool means. Okay. So let me explain to you what representative sets are, why do we need it, what are they, and how are we going to compute them. So first let's see why. So I'm sure all of you people have seen dynamic programming for Hamiltonian path in your courses. At least I know this exists as an exercise in CLRS dynamic programming chapter, maybe to some 22 point something, I don't remember very well, but it does exist as an exercise in this. But if you have not done this exercise, let's do this exercise. So how do you find a Hamiltonian path in a graph? So basically what you have, so you have a double matrix, V1 to Vn, and 1, 2, 3, I, n minus 1. So you have 2 cross 2 matrices. On the rows, you have vertices. On the columns, you have the size of the path which you will try to store. And what are we trying to store at a particular index? Let's see. So suppose I have a vertex Vj and column I. What I'm going to store at this place is the following. Paths of length I ending at Vj. What I'm going to store? Paths of length I ending at Vj. This is what I'm going to store. For example, this is a path which of some particular length which ends at Vj, so we'll store that. There's some other path which is there, I'll try to store that. But what we'll try to store is sets, not sequences. What I mean by this, maybe you can have a same set of vertices, but you could have a different path because you moved 1, 3, 5, 7 or 1, 5, 3, 7, right? But as a set of vertices, they are just same set. It's just that because what did you say to find an algorithm for k path is like n choose k and k factorial. So I'm trying to get rid of this k factorial first. Okay? So rather than storing all permutation, if possible, I'm going to store a set, not the sequence or the sequence in which they are visited. So what does it mean? Is like, look at this, right? This is the same, it's the same set of vertices which is visited, but I'm not going to store both as my subset of vertices. Okay? So this is another example. So two paths that use the same set of vertices but visit them in a different orders are equivalent for me, right? So what is an equivalence relation I defined? I said, look at two paths. If they have the same set of vertices, but maybe they are visited in a different order, for me they are equivalent. Okay? So I'm just going to keep one of them. Notice one, like if finally here, if for any one of the last index, if I have some set, it means there is a way to get a Hamiltonian path, right? That's very clear. In which order, I don't know at this point of time, but in fact, we can store one order for sure. Let's see how. So what is a path of length I ending at Vj? Is basically how will I store it? So imagine that you are going to fill this matrix. First you fill the first column, then you fill the second column. So you already have filled first I minus 1 column, and I'm trying to fill ith column. So what I'm saying, paths of length I ending at Vj is basically paths of length I minus 1 ending at some vertex u, avoiding Vj. But u has to be what? Neighbor of Vj. So let's just add this. U should be neighbor of Vj, right? So what are we going to store? So I'm going to look at, step back, look at one of my neighbor. I say, hey, I go back. Oh, this guy is storing a path of length I minus 1. Look at the sets. First of all, it should not be using Vj because I want to take that, and from u, I want to extend to a path of length I to Vj, right? So this is what we do, right? So here I have many ways, right? So potentially, how many solutions can you store? You could store as many as n choose I. But now notice, we don't have I factorial because we are only storing one set. So even if there were many paths on the same vertex set, we're just storing one set. And how you can get one sequence is that, look, every time I have a set of vertices, I think that they are in a sequence. And then I add myself at the end of the sequence. So you start with empty set. First is same vertex. What this tells us? Paths of length I minus 1 ending at u. Suppose these are in some particular sequence, fixed sequence. Next, what I will say, take this set, I will add a Vj at the end, right? So then I have got a path of length I or path. There could be many paths on the same vertex set, but at least I have been able to store or path. So basically, you can think that you are storing a representative on the equivalence relation which you have defined. So what is the two sets or two paths are equivalent if they use same set of vertices. And from this equivalence class, I have stored exactly one path. Okay? So this is my dynamic programming, and this is what you do when you do. Okay? So how much time does this take to find a Hamiltonian path? It could take as many as 2 power n, because you could have in ith, how many sets you can have of, you could have n choose I sets, but at most n places you're storing. You can fill these entries by looking at the previous entries over your neighbor, which is again number of neighbors is upper bounded by n. Look at these sets, and proportional to that you can fill your table. So you can show that the whole table can be filled in 2 power n time. And of course it can take you 2 power n space also, because you're storing all the sets. And this algorithm was what was known in terms of running time for last 30-40 years, till in 2010 this algorithm was improved. Okay? And notice one thing, in this algorithm there's nothing about directed graph or undirected graph. It doesn't matter. If it had been directed graph, I would not say neighbor, I would say in neighbors. That's it. And this algorithm will still work. Okay? There is also a version of this algorithm where we do not need to store everything, but it can work in polynomial space, but for that we need some kind of inclusion exclusion, which we will see later. Okay, so now if you're trying to find a path of length at least k, what should you do? Just restrict your algorithm to just first k columns. That's it. But then that algorithm will run in time O star n choose k, right? So if I'm looking for a k path, I can get an algorithm. So in the beginning we had n choose k into k factorial. I already have been able to remove this k factorial term by doing this dynamic programming algorithm. Okay? For us, it is important to know this dynamic programming algorithm. So if you did not understand some aspect of this dynamic programming algorithm, please ask. Because this is one algorithm which you need to have in your mind for next 2 lectures, this lecture and the next lecture. Because all I'm going to do, make this dynamic programming algorithm faster and faster and faster by not storing everything, but storing something which is much smaller than n choose I. Question? Any question? Or everybody understands this dynamic programming algorithm? If you even did not understand, you can go back and check. Okay, so worst case running time could be all bad, all as much as n. But let's ask ourselves, do we really need to store all these sets? Or something, look, first of all, what did we say? So it could have been n choose I into I factorial if we had stored all paths. But we said, okay, let's forget it. We don't have to store all, let's keep the set. So we already reduced from n choose I into I factorial to n choose I. Now my next question is, do we need to store even n choose I, or we can do something better? So in the ith column, we are storing paths of length I. Let p be a path of length k. Okay, so now we are only interested in path of length k. And there may be several paths of length I that latch on to the last k minus 1 vertices on p. Why are we storing all this? Because we do not know the future. We say, hey, look, because I don't know the future. What do you mean by future? I say, look, the paths which I'm storing, they could be prefixes, which could be a useful prefix for a k-length path, which will come in the future, right? So what I'm asking is, there may be several paths of length I that could be used as a prefix for the last k minus I guys. Right? So what you do, so at this point of time when you are storing something in dynamic programming table, what are you trying to store? You try to store all possible partial solutions. And what do you mean by possible partial solution? These are those set of vertices which might be might be possible to extend to a k-length path, right? So I said, I don't know the future, so let me store all possible things. And we said, oh, look, if first to last on this set of vertices are there, then any path, since this and this is disjoint, I can take this and pass this up. And that is what we try to do. Okay, so now I'm asking that, okay, I may be keeping so many paths. Do I really need to keep all these paths? Maybe I can use the same set of vertices for many, many paths for the future, in the whatever path is coming in future, or the suffixes, I can have much lesser number of prefixes to keep. And it doesn't sound that we will be able to achieve this, but actually we will see as it follows that actually very small number of this n to the I objects is actually necessary to maintain this kind of property, the path property. Okay, so what I mean by this, so we'll just store as we'll try. Our whole objective is to currently we're storing lots of paths, partial solutions. We want to store as few as possible without losing any path, right? If the instance was an yes instance, we would like to maintain it to be yes instance, right? We do not want to lose any paths. So for example, let's look at this. This is, suppose we have a path on 7 vertices, okay? And let's consider it broken into first 4, into the first 4 and the last 3 edges, okay? So this is the first 4 guys. This is the red, the pink color, or what is it? Magenta is our breakpoint. So this is the first 4 and this is the last 3. Now, look, this last 3 could be useful for, this last 3 can be completed using this path, or maybe using this path, or maybe using this path, or maybe using this path. So I have kept the last 3 things which will come in future, right? All these guys can complete it to a path of length. So ideally, for everything which is last, I would like to keep one of these guys into my solution. But so this is like a fixed future. So what is a fixed future? Some vi plus 1 to vk. So this is my fixed future, and I'm saying what all the things which is in my currently which I'm storing, that maybe I can throw away some of these guys and still have the following thing. Okay, whatever the future you give me, I have something stored such that I will be able to get a path. That's what I would like to do. What is the goal? The goal is to have this. I want to shrink my number of partial solutions with the following property, that whatever may be the last part of your path, I have something stored in my small set such that this and this will give you a path. Okay, so I'll formalize this concept in a much more clear way in a minute. Okay, so let's try a different example. Okay, so here, if this is a fixed future, you have so many possible partial solutions, and ideally we would like to store for each fixed future only one of them. But the problem is, even if I do this, here's one more example, right? So I'll put the slides so that you go through it before you come tomorrow at 4 o'clock. So for any possible ending of length k minus 1, we want to be sure that we store at least one among the possible many possible prefixes. So what we want to store for any possible ending of length k minus 1, we want to be sure that in our partial solution there's at least one prefix which is stored. That is all our goal is. But this could be as bad as n choose k minus I, because try all last k minus I, for each of them I store one thing. So, okay, but the hope for saving comes from the fact that a single path of length I is potentially capable of being a prefix to several distinct endings. Okay, so for example, so I'm just trying to motivate you why it could even be possible. I'm not even giving you formally how we will do this, which we will see today or tomorrow. So for example, look at this, right? Now, look at this. These are different paths, right? But same path can take care of all these guys, right? So if I had stored this magenta color path, then we say, hey, if you gave me this path, then I say, hey, here is it. You just combine them, you will get a path of length k. If you gave me the second one, I will still produce the same thing, and that's perfectly fine. Similarly, the last path, I will still give you the same thing and say, hey, here it is. It takes care of everything. So algorithmically, what is the kind of question we are trying to ask? So let's try to understand that first. So what are partial solutions? These are paths of length j ending at subvertex vi. So what we want, a smaller representative family with the following property. So if I have a path like this, some vi, right? And these are k minus j vertices and the first j vertices, such that what we want. So if you have some k minus j vertices for which I have a partial solution in the bigger box, means I can patch them and get a path, then what do I want in my smaller family is that, well, I also have a path in my smaller set such that you can take these two and patch them and get a path of length k. So that is my whole goal. What is my whole goal? Is that I have a bigger set of partial solution, right? If there is, you give me any ending, and if there is any way to extend this from the bigger set, then there is a way to extend this from my smaller set of representative. Okay? So that's my whole goal, right? So combinatorially, this is the question which we are trying to address. What is the question? I have a partial solutions, paths of length j ending at a particular vertex. Okay? And what I'm saying that, look, you give me the last ending such that I have someone which together with this gives me a path of length k. Then in my smaller set also I have someone which together with your whatever ending you gave, this guy and this guy can combine together and give me a path of length k. So that is a combinatorial question which we are interested in. So I do not want you to understand the answer, but at this point of time I want you to just understand the question. Is the question clear to you? Okay, so this is what the kind of questions which we are interested in. So let me so basically we would like to store at least one path of length j that serves the same purpose. That's the whole goal. And so basically a combinatorial question which we are interested in. So you have a big family of p size subset of n, big size, S1 to ST. Think of them as your paths, like first j length paths. Want a small subfamily f hat of f, which is a subfamily of this, such that for any x, now I have made my questions even more harder for myself. Before I said, look, if there is a path for which there is a path, they can combine a path. I said, no, I don't care anymore. What I'm saying, for any x subset of 1 to n of size k minus p, right? If there is a set S in f such that x intersection S is empty, whether they form a path, they don't form a path, I do not care. All I'm asking, you give me any k minus p size set such that I have a set in my family such that both of them are disjoint, they do not intersect. Then there is a set S hat in f hat such that x intersection S hat is phi. That is what my goal is. Look, now I'm asking even more harder set of, I'm putting much more constraints. I have forgot that they have to form a path. I said, look, if they form a path, then clearly this and this are disjoint vertex sets. But I'm saying forget about this. Look at my set of partial solution. If for any set outside, I have a set here which is disjoint, then in your subfamily, you should have someone which is disjoint. So this is asking even much more stricter than what the path question was. So if you did not understand the analog from the partial solution, you can just think of this as a combinatorial question. You have a universe over which you are given a sets S1 to ST, right? Where each set has size p. And what is the goal? Our goal is to find a small subfamily of this with the property that if there is a set S in, for any x of size k minus p, if there is a set S in f such that x intersection S is empty set, then there is a set S hat in f hat so that x intersection S hat is equal to phi. Okay? So x, because why did we have to go and generalize this? Because I don't know what set in the future can come. So let's assume that anyone can come. For example, if you had a complete graph on n vertices, then any set from outside can come, right? So if I'm trying to make an algorithm which works for every graph, in particular it should work for complete graph also, right? And there x on k minus p vertices could be any set, right? So it is a good assumption to make. So could be any subset. If what is S, this is a valid patch, then what I'm saying, then this is a guaranteed replacement for S, right? So if you go back, what I'm saying, basically, second half of solution, this X of K minus P is like second half of your path, which could be anything. If there is a way to patch them, then there is a guaranteed replacement to patch them. That is the whole goal. And small, so A is like n choose B at most, because as I saw, n choose I. And what will be small will mean K choose B. Okay? So small will mean K choose B. Okay? And this is a theorem which was proved by Bolabus in 1965. And in tomorrow's lecture, we'll see A. We'll not see a proof for this until I have put up my exercise, which will, I think I'll request the organizer to put this. And we will see how to, if I give you a family, how do you compute this without looking at the future? Imagine I gave you S1 to ST and say, hey, give me a small subfamily of size K choose P, which will do this job in a very good way, so that we can use it for parameterized algorithms, right? How will we do this? So that is what we will do tomorrow. First, see how to compute this object of this size, and then we'll see how to use it to design an algorithm. Okay? If you think about yourself that if you had such a nice algorithm, then think about yourself that how will you use it to make your dynamic programming algorithm which runs in time FPT. So this is something to think about. It's not very hard, but if you had such a small object which is good enough for your purposes, how will you use this small enough objects to design a parameterized algorithm? Okay? Thanks.